Early in our study of fluid mechanics, before we become concerned with the motion of fluids, it's important to understand pressure and the forces that pressure exerts on solid bodies. To begin, we need instruments that measure pressure. This tire gauge, based on the Borden tube principle, reads the tire pressure as a gauge pressure, about 34 pounds per square inch, psi, or 234 kilopascals. Gauge pressure is the increment of pressure above atmospheric pressure. This is another instrument based on the same principle, but designed to read absolute pressure. It reads about 14.4 psi when open to the atmosphere at the altitude where these experiments were done. If we apply pressure above 1 atmosphere, the reading increases above 14.4 psi. As a vacuum pump draws the pressure down, the reading tends towards 0 on this absolute pressure scale. Both these instruments operate on the Borden tube principle. The curved tube is connected to the high pressure being read. A higher pressure tends to straighten out the tube and vice versa. The end of the tube is connected to a linkage that drives an indicating needle on the face of the pressure gauge. There are other instruments to measure pressure, such as this diaphragm-type transducer. A pressure difference across the thin metal diaphragm causes it to flex and changes the internal capacitance of the transducer, which is sensed electrically and converted to a pressure reading. This is a modern piezoelectric pressure transducer. Its tip contains a crystal that responds to pressure changes by generating an electric charge. The amount of charge can be converted to a pressure reading through calibration. Hydrostatic pressure increases linearly with depth in a fluid. You can feel the pressure increase just by diving to the bottom of a swimming pool. Hydroelectric dams must be designed with this in mind. They're much thicker at the bottom than at the top in order to withstand a large increase in hydrostatic pressure. The water enters the hydroelectric turbine at high pressure from the bottom of the dam and retains enough kinetic energy to produce a water jet when discharged at 1 atmosphere. Watch the colored pressure contours on the supporting columns of this oil rig CFD simulation. As the water level rises due to waves passing, so does the pressure level on the columns. Deep-sea research craft like the Johnson Sea-Link submersible must be made immensely strong to withstand the pressure at the ocean floor. This doesn't bother the strange creatures that live there, however, because the pressure inside their bodies is the same as the surrounding pressure. If that were not the case, they would be crushed instantly. Here's a popular little experiment that demonstrates hydrostatic pressure in the atmosphere. We boil some water in this metal can, then cap the can and sit it in cold water. As the steam condenses back to liquid inside the can, the internal pressure drops and the can is crushed. It's tempting to think that the sides of the can are sucked in, but in fact, the can is crushed by the weight of the column of air over 100 kilometers high that sits on top of it. Hydrostatic pressure naturally leads to a fundamental way to measure pressure, by the height of a liquid column. These two manometer tubes are connected to different points in a venturi. With no flow, the height of liquid is the same in both tubes, indicating a constant pressure along the center line. But when water flows through the venturi, a low pressure occurs at the minimum area according to Bernoulli's principle, which applies to fluids in motion. We can see that the pressure is lower there than upstream because it supports a shorter column of water. Measuring blood pressure requires another type of manometer, a sphygmomanometer. It measures two different pressures associated with your bloodstream, systolic and diastolic. They're usually expressed one over the other, as in 120/80, which is considered normal. The 120 and the 80 are the heights in millimeters of a manometer column of mercury. Thus, the height of a liquid in a manometer defines a unit of pressure measurement. Hydrostatic pressure in the atmosphere is responsible for the buoyancy of a hot air balloon. The balloon is filled with hot air that is less dense than the surrounding atmosphere. According to Archimedes' principle, a buoyant force acts on the balloon equal to the weight of the air it displaces. Once the balloon weighs less than this buoyant force, away it goes. The same principle holds for this tethered helium balloon. The net upward force in the balloon due to buoyancy appears as a tension in the tether, a fluid statics problem. Cut the tether, and the balloon accelerates upward. This works as well underwater, where gas bubbles rise due to buoyancy and deform by interacting with the surrounding fluid. This toy boat floats stably in the bathtub because most of its weight is below the water level. We can make it unstable, however, by adding weight above the water level. Eventually, the center of gravity rises enough that the boat overturns. Likewise, the box in this CFD simulation is top-heavy, so it's unstable and flips after being dropped into a tank of water. Once the heavy side is down, it floats stably. Temperature differences can also induce instabilities due to buoyancy, as in this CFD animation of Baynard cells in water sandwiched between two plates. The top plate is cold, the bottom plate is hot, and the combination drives a recirculating flow. You can see Baynard cells in a simple experiment in a frying pan, where a thin layer of cooking oil is heated from below. The striped background helps to visualize the array of cells that dimple the surface of the oil. Pascal's law says that pressure applied to a confined liquid is transmitted equally to all the confining surfaces. This principle underlies hydraulic power, as shown by this tractor. A hydraulic fluid pump, powered by the engine, increases the pressure over a small area. The pressure is conveyed by hydraulic lines to move a larger cylinder with considerable mechanical advantage. Hydraulic power is very important in many applications, ranging from earth-moving equipment to aircraft control surfaces. When only gravity is at play, liquid surfaces in the laboratory are flat and horizontal. However, when we spin this container of water, it rotates as a solid body, and centrifugal acceleration distorts the free surface into a parabolic shape. An accompanying CFD simulation shows colored pressure contours, revealing that the pressure indeed rises linearly downward from any point on the surface, just like the case for a motionless body of water, according to the principle of hydrostatic pressure.